Oh, you watched that?
Yeah, we watch Boruto. I think we have a subscription to Crunchyroll at the moment.
I haven't. I've been told not to watch Boruto.
You've been told not to watch Boruto? See, all right, so my friend was like, he was really excited when Boruto first came out. He's like, you gotta watch it. It's really important. Watch the first 30 seconds. Be really careful. You gotta watch the first 30 seconds. It's like a flash forward, blah, 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 blah. And so I did, and I got all excited about it, and I talked to him about it. And then he just stopped watching the show. He's just like, no, it's filler now. I'm gonna wait until it's all done. It's like, what? You gotta go? We're not done.
Oh.
Oh. Oh no, I'm sorry. I know it's confusing. I actually covered material the first day. Yes, yes, yes. I know. Like it's the first class you've had where you're actually getting like instruction the first day. I know. I'm very countercultural here. What can I tell you? But
Yes, I was told not to watch it.
Oh really?
Yes, it's just because like if you enjoyed Naruto a lot, which I do. It says that it makes Naruto and all his friends kind of look weak.
Oh, that is not true. No, that is not true. No. Everyone improves. Now, it's like the next generation is more adept at gaining skill than the previous. That's true. But like Naruto and Sasuke in the new series, they're stronger than they were in the previous one, and so forth. And there's these trans-dimensional aliens that are pretty cool. So there's all that. But anyway, this is probably not going to help you with calculus. I have managed to put one of my proudest moments was I wrote a problem about Neji in Calculus 3 that was based on his weakness. So if you've watched Naruto, he has his blind spot, this particular part. So he's like 300, like full sphere of defensive capability, but there's just like this one place where he has a blind spot. I made a problem on that.
That's awesome.
I spent a long time on that.
That'd be cool.
I don't teach Calc 3 here though, so I've got no place to, I can't really, in good conscience, put that in your course. So, okay, so I want to talk a little bit about history and calculus. I won't talk too long about history. But so calculus, as we understand it, is largely due to Newton and Leibniz, and they did what? Their work was, I think, 1680, 1700, something like that, is when these things got sort of coalesced. But it wasn't in a vacuum, right? So, the work of Fermat and Euler, well, not Euler, Euler's after, but certainly Fermat and others pushed the forefront of like algebraic understanding in Europe. They, of course, learned from things that were done in the Arab world. And then, of course, in the ancients, there's ancient mathematics, in all cultures, Babylonians, the Chinese, the Greeks. And there have been aspects of calculus that have been known since ancient times. Like, for example, Archimedes is a very interesting character. He did things like approximate pi, which is, of course, the ratio of what? The circumference to the diameter in a circle, right? So he inscribed inside a circle regular n-gons. Like you could think about putting a square and then putting a five-sided thing. And so, and if you just kept going finer and finer, you could calculate the length of the line relative to the length of divide by the diameter. And so if you calculated the total perimeter of that and divided by that, well, that would give you an approximation of pi, right? So Archimedes understood that if you wanted to get closer and closer to the true pi, you should just make more and more sides. That's kind of the concept of a limit. As you let the number of sides go to infinity, that becomes a circle in some sense. Well, that's a kind of limiting idea. That's a precursor to some of the ideas in calculus. But Archimedes is a very interesting character. He also invented number systems to count. There's an ancient paper he wrote to a king called the Sand Reckoner, where he invents a number system to count the number of sand particles on a beach or something, But back then, you had to be somebody with just an unparalleled intellect, a true genius, to do these kinds of things, right? So the ideas of calculus, in particular the idea of like approaching something from a limiting sense, only the most brilliant people could even have hope to do something in ancient times. But there have been, and also in ancient Chinese mathematics, there have been things that are essentially calculus, but these were always hidden from the general public because they just required just a brute strength intellect to do. Nowadays, we can teach calculus to everybody. It is, in fact, a required subject, at some of like the Ivy League schools and stuff. Like there's an expectation that a university student has taken calculus. I've suggested that in meetings with administration where I used to work, and everyone looked at me like I was crazy. Because it is kind of a silly thing. Like we have so many people, like 40% of the population comes to university now, right? And 40% of the population probably doesn't need to take calculus. Because calculus is really something we need for science and engineering, right? Maybe not so much for somebody in like exercise science or biology. Well, biology's, I don't know. Anyway, my point to you is just that there have been aspects of calculus known to the ancients, but really the mathematics which was needed for calculus, as we're going to study this semester, really only came into being sort of after the Dark Ages in Europe, maybe about 1500 to 1700. The algebra, the understanding of number systems, like the decimal representation of numbers, you take it for granted, right? But there was a time before we had that. And it's only maybe, if I understand the history correctly, 50 or so years before Newton that decimal representations of numbers became widely known in like university. So that's such an important thing, because before then, what would you have done? You would have done something like use rational numbers to describe approximations. If I tell you 13/50ths and 20/70ths, which one is larger, which one is smaller? 13/50ths or 20/70ths, which one's bigger, which one's smaller? Like, I don't know, I just made it up, right? But on the other hand, if I say 0.0079 and 0.0123, and I say which one's bigger, which one's smaller, you immediately know the second one's bigger, right? I mean, you could just see it. So if you're making calculations which are about finding finer and finer approximations to things, the decimal representation of numbers is mission critical for like gaining understanding. And this is what Newton and Leibniz had to work with. They also had a mastery of polynomial algebra. And anyway, what I'm trying to say is when Newton and Leibniz discovered calculus, it wasn't in a vacuum. The stage was set for them to do that. But they're, of course, both brilliant intellects. That's also true. So anyway, that's just a brief sort of comment about how we got here. And the other thing I will say is I try to give a somewhat scholarly approach to calculus. I try to explain to you where the ideas are from, but I really don't have a full history of calculus in my notes because it's really difficult to say who did what first when you go back to like basic calculus we learned this semester, because they kind of all did it. And I don't think, if you ask the question, who discovered the chain rule first, for example, it would be a very difficult question to answer with authority. But anyway. Now, of course, one of the things that motivated the invention of calculus was physics, right? So instantaneous rates of change. So if I start at my house in Tuscaloosa and I go here and it takes me an hour, it's about 60 miles. How fast did I go? 60 miles an hour, right? So when the state trooper stops me at exit 25 and tells me that I was going 90 miles an hour on 59, and then I say, I'm sorry, sir, but every day I start at my house at 9 o'clock and I get to school at 10 o'clock, clearly I'm going 60 miles per hour. He's probably not going to care. In fact, that's probably a quick way for me to have a talk outside the police car. But it's instantaneous velocity that the police measure, right? It's the idea of how fast you go over just a very brief instant of time, right? Think about what that is. It's your change in distance over your change in time, where this change in time is getting smaller and smaller and smaller, right? Now, what if you made the change in time be 0? Well, then algebraically we're into trouble, right? We can't divide by 0. And yet this is the tension. Like, this is exactly the kind of thing that physics wants to discuss, is what happens when you have a rate of change where you're not over just a finite increment time, but over an instant of time, right? So to capture this idea, Newton introduced something called a fluxion. So a fluxion was something like, I don't know if I can say it right, that. It's something that is very, very, very small and yet not 0. It's not really a number. It's something smaller than any number. So this was just something that sort of Newton, and in some sense Leibniz did something similar to this. They built calculus over this kind of idea of a fluxion. But this is very non-rigorous because what is it, right? Well, it's something very small, but it's not 0. And so we have replaced this rather sort of heuristic idea with what's called a limit. A limit allows us to capture this idea that something is going to 0, but it's not actually reaching 0. So limits have replaced this idea of fluxion. And so that's why, to start with in this course, we're going to basically study limits for a little while and try to understand those. So there were two major problems that motivated calculus, just to give you kind of an overview of the course. There is, probably been talking out of screen, but you guys are both here, so, well, sorry, YouTube people. The two major problems in calculus are the tangent problem and the area problem, right? So the tangent line and the area problem. So the tangent line problem is, if you have a curve and you pick a point on the curve, right? How do you find the tangent line to that curve, right? The tangent line is something that just touches the curve and it just kind of lines up with the curve. It's easy to say for a circle. We've studied tangent lines for circles since a very long time. Tangent line to a circle is a line which touches the circle at just one point, right? So that suffices to define a tangent line for a circle. That definition doesn't work for more interesting curves, right? Because this tangent line to this curve, it doesn't touch it at just one point, right? It also touches it where? Like down here. So there's the point of tangency, and then there's also this other point. So this is one of the first things we'll describe, is how do we find the tangent line to a curve, all right? And we're going to need limits to do that, okay? So the problem of the tangent line is largely answered by what we call differential calculus. Differential calculus is the first story arc in the course, all right? And in a nutshell, we're going to learn how to calculate derivatives, and we're going to learn how they solve the tangent line problem, but they also give us insight into instantaneous rates of change, like that state trooper likes to measure. And then, once we're done with that, we study the area problem, right? And the area problem is essentially just to find the area bounded by a curve. So the standard problem is something like this. You've got a function, and then the question is, what's the area between, say, A and B, like this, right? What's this area bounded between the curve y equals f of x and the x-axis? So that is the question. I mean, if the line were flat, we'd know the answer. Length times width, it'd be a rectangle, right? If it was just a triangle shape, we could calculate that, 1/2 base times height, right? But what about more interesting shapes? How do you find the area of a shape which has curved sides? Okay, this is the problem that we answer in the second half of this course, and the answer is given to us by what's called integral calculus. All right, so that's the second half of this course we'll get to. Ultimately, the answer to that is given by something like this: integral from a to b, f of x dx, this is actually going to be the area. I'll just tell you that. Right now, it's just a bunch of kind of meaningless symbols on a board, right? What does that even mean, this thing I wrote? Actually, have you guys had high school calculus? Did you have calculus in high school is my question, really. Maybe? You don't remember? I think that counts as a no. No, no, I know. It's like you're trying to suppress the memory of high school, or no? Yeah. In any event, this S is actually for sum. It's sometimes called a continuous sum. And this is called the integral of the function, actually the definite integral of the function. We'll learn at the tail end of this course, we'll learn how to calculate this. Now, all right, my question to you, I'm just telling you, these are the central motivating problems for calculus. Find the tangent line, calculate the area under a curve, all right? Do you think these problems have anything to do with each other? Like, should understanding a tangent line allow you to calculate the area under a curve in an easier way? I don't think so, right? I think your answer of no is completely legitimate, and it's why mathematicians didn't notice it for millennia. Even great minds like Archimedes didn't see that. Partly because they didn't have the algebraic. Before the time of about Fermat or so, we used to write out algebraic equations in sentences. Like, take the quantity and multiply it by, take thrice the quantity and subtract the square of twice the quantity. And that's what you'd have to do to express 3x minus 2x squared. You'd have to write it out in like sentences. Can you imagine that? I can't imagine that. That's why only mathematicians did math back then, right? But now we have algebra, which everybody can understand. It's made math accessible to everybody who just, who wants to do it. I can't teach math to anybody who doesn't want to learn, I don't have the technology, and even if I did, it wouldn't be ethical, Although I wondered if you could get collars for students that you could like zap them when they don't pay attention, and then you could do stuff. You'd have to run it through the IRB, right, to see if it was. You'd have to get them to sign consent forms and stuff. But wouldn't it be interesting? I'm just kidding. But the answer, though, shockingly, is yes. In fact, these problems are linked. It turns out that we'll be able to use the opposite of differentiation to actually find a way to basically algebraically calculate the area under certain curves. This is the great discovery of Newton and also Leibniz, what's called the fundamental theorem of calculus. It is shocking. It really is. That's one of the things we'll learn at the end of this course. I learned it. I learned how to do it in calculus, right? I think I had calculus 2 at that point. And then I remember talking to my brother. Like I told you guys earlier, he's now a mathematician. I think we were teenagers at the time. Maybe I was probably 19, he was 17, something like that. I remember talking to him and going, just sort of dawning on me, wait a minute, why is the fundamental theorem of calculus true? Like, we've had the course, we had through calculus 2, we knew how to do all the calculations, but why is it true? It is really quite striking. But I actually will show you a proof in here of why it's true. So hopefully you won't be like me without an answer. Now, a very nice lady taught me Calculus 1 as an independent study over the summer. She had not taught calculus in a decade. So my Calculus 1 was pretty weak. When I got to Calculus 2, I remember going to ask the professor what an exponential function was. Do you guys know what an exponential function is? See, you're already ahead of me at the end of my Calculus 1. But that Calculus 2 instructor, you know what? He made me feel at home in his office. I came and I asked him all kinds of stupid questions, and he encouraged me to become a math major, actually. And at the time, I was more interested in physics and engineering, but eventually, I think he had his way. Well, here I am, right? By the way, the term calculus originates from the ancient Roman practice of using tiny pebbles to calculate. So there you go, if you're wondering, calculus. It's also interesting that the advisor to Newton, his name was Isaac Barrow, essentially solved the tangent problem, but didn't quite, I mean, he had it, but he didn't popularize it. So this is the thing, is there have been like different bits and pieces to the story I'm going to tell you this semester, which were studied by various people, but nobody put it all together in a way which everyone else could understand until Leibniz and Newton. So that's why we give them the credit. At the end of chapter 1, I have a list of basic equations in physics, all right, on page 13. Newtonian mechanics, Lagrangian mechanics, electricity and magnetism. The boxed equations, these are the fundamental equations that we define physical law with. If you look at them, they're all written in terms of derivatives. All right, so instantaneous rates of change, or just rates of change, doesn't have to be with respect to time, all right? All of these equations, they're calculus-based. That's why calculus is important to a university education, because basic physics is all phrased in terms of derivatives. Admittedly, the frontier of physics requires much more mathematical sophistication these days. All right, I'm going to shut up about that. Let's get to chapter 2 here. So, set theory. Let's see here. When did I start? 12:30 I start?
Yes, that's when it's...
So I have until 2:30, right? 1:45. Oh, 1:45, okay. You gotta watch me, I'll try to add time. So today we're mostly just introducing notation. I'm not really teaching you, there's not much of we're not learning any skill today. We're really just learning definitions and terminology, right? So set theory. So what can we do with, what do we mean? Two sets are equal what, when? What does this mean? This means the sets S and T have all the same elements, right? That's what we mean by set equality. All right. Some notation. Here's the notation. We write this like X such that X has property P. So these curly brackets are notation we use for sets. This bar in the middle is to be read such that, right? So here, let me give you an example. We could let S be equal to X, an element of the set of cats. So this notation right here means is element of. That fun.
The different S.
Oh, yeah, that's just my, I just put, that's just my S, my capital S. I decorate it. There's nothing especially special about that. But this means element of, all right? X is an element of cats such that X is evil. All right? So in principle, this is a subset of the set of all cats. But I would argue that you could write this. This is equal to cats. In other words, what I'm trying to tell you is the set of all cats such that you have an evil cat. Well, that is all cats, because all cats are evil.
I get what you're saying.
Mm-hmm. Can't really argue with it. I'm just kidding. All right, so example 1. let's see here. Here's a different example too. How about this? S equal to x in n, the natural numbers, such that x is equal to y squared for some natural number y. So I'm introducing some things as I go in this example. So this funny looking n, this is the set of natural numbers. So n is 1, 2, 3, 4, and so forth and so on. So let's see here, this example too. So I'm saying S is a set. It's the set of natural numbers such that what? Such that x is equal to y squared for some natural number y.
Are we supposed to put that second line?
Which second line?
On the end, on the left side of the end.
Oh, I just write one.
Is that even an int, or is that a symbol?
This is, well, I mean, it's n, but it's, okay, so notation. This is the natural numbers. This is the integers.
Okay.
This is the rational numbers. This is the real numbers. This is the complex numbers. So yeah, that's not just an n, it's not just a z, it's not just a q, it's not just an r, it's not just a c. They're funny. These are, okay, so in textbooks, sometimes they make these bold. They make these like a bold letter, but I can't make bold on the chalkboard, so this is a good choice. Now, I edit my notes in something called LaTeX, right? So like the LaTeX command for this would be something like math boldface n. I think there's like maybe like a hash here or something, but if you're using what's called LaTeX, but we can talk more about that after class or something if you're interested. I mean, I can give you the source code to my notes if you want to play with them. It's up to you.
So are we going to need the Z, Q? I know we're going to need the all real numbers.
Oh yes, well, you need to know what these symbols mean because I will refer to these number systems to characterize equations or solution sets or different things. So this is part of our like basic lexicon of things we refer to. Again, the natural numbers. First one. This is what are called, these are integers, right? The reason for the z, it goes back to when this notation was popularized. German mathematics was very, very influential. And the word for number in integers in German is Zahlen. So it's from that. I forget exactly where the Q comes from, but anyway, that's rational numbers, basically fractions, right? And the real numbers, well, we identify that with the number line, right? Minus infinity to infinity. Think about that as being the real numbers. And then, of course, there's complex numbers, which are a plus ib, where a and b are the real part and the imaginary part, and this I is this number that squares to -1, right? So you guys have seen in complex numbers just a little bit here and there in the algebra sequence, right? But you never really kind of dwell on them that long, do you? No.
I squared and the a plus ib.
Mm-hmm. Yeah, now our focus in here is on the calculus of real functions of a real variable, but we do deal with certain questions of algebra, and to understand algebra completely, we have to talk about complex numbers. It's just unavoidable, all right? So I have to talk about it a little bit, but the focus here is not on complex numbers, of course. So, all right, now that I've shared with you all of this terminology, can you tell me better what this set S is? What is that? Can you start listing numbers in there for me? Let me ask a more specific question. Would 3 be an element of S? Is 3 an element of S? Question mark. All right, so if so, then 3 would be equal to y squared, right? For some natural number, right? But what happens if you solve that for y? What do you get? Take the square root of both sides, right? What do you get? Yeah, square root of 3 is plus or minus. Well, it's square root of y squared, right? What is the square root of y squared? It is y sometimes. It is minus y other times. But so I would say that it's absolute value of y, right? No. See, because either so basically plus or minus the square root of 3, both square root of 3 is the point. But you're right. I mean, y is half the answer. And it is. But the thing is, so y is equal to plus or minus square root of 3, right? And those are not natural numbers, right? So that's actually my reason for talking about this, is to introduce this notation for you. This right here means not an element of. All right? So 3 wouldn't be in there. What is in there? So if you think about it for a second here, 1 is in there, right? Because 1 is equal to 1 squared, right? So we can take y equals to 1 to get 1 in the set. What else is in there? How about if we put y equals, we get 4, right? 9, yeah, 16, 25. You get the idea here. So this set S, it is actually the set of all squares. That's what S is. So I'm just introducing this example as something for us to chew on to understand this element of idea, not an element of idea, and what we mean by this. This is called, this notation up here, it's sometimes called set builder notation. Sometimes people call it roster notation. All right?
So everything in between those brackets, roster notation?
Yeah, the totality of what's, this whole concept is roster notation.
Oh, I got it.
Yeah. Or set builder notation. Now, I guess maybe people, I think maybe when people say roster notation, they're often aiming for when we talk about a set just by listing the elements of it between curly brackets, right? Kind of like the roster for a team.
Oh, I got you.
Yeah, that would be a reasonable reason to use that word, right? Usually in mathematics, when we choose a word, it means what it sounds like. Usually. However, I would caution you, if you hear a mathematician use the word simple, simple has like dozens of complicated technical definitions in various contexts of math. Okay, so next thing we should talk about in terms of set theory is the Cartesian product. Have you guys ever heard of a Cartesian product before? It's not that complicated, really. You've actually already been working with it. Maybe just think of it that way. So if A and B are sets, then A cross B is the set of x comma y such that x is an element of A and y is an element of B. So this is a Cartesian product. This is the Cartesian product of A and B. That's roster notation, right? Oh yeah. So here, let me give you an example. I'll use roster notation. Okay. So suppose A is equal to the set with 1 and 2. All right. And suppose B is the set with, I don't know, 3, 4, and 5. All right. We could look at the Cartesian product of the set A and the set B. What would that give us? So I'll write it out symbolic. We're going to take, and we could even use the letter A and B. Little b, such that little a is in big A, and little b is in big B. That's a pretty typical notation. We use the little letter for the element of the set and the big letter for the set. A lot of times, textbooks, mathematicians use this notation. Okay, so I'll get the ball rolling here. I would point out that 1, 3 is one of the elements in this set. What else? 2 and 4. Okay, good. 1 and 5. 1, 4. 1, 2. 2 and 3. 2, 3. 1, 2, 3, 4, 5, 6. We're done. See, I happen to know, fun fact, for finite sets, the number of elements in A cross B is the number of elements in A times the number of elements in B. So when you're working with a finite set, it's pretty easy because, well, let me visualize this for you, right? So we could draw a picture of this, okay, in the following sense. If I draw the plane, right, which is x this way and y that way, right? We can visualize these points, right? They're, let's see, here's 1, here's 2, here's 3, 4, 5, right? So we have this point, right? Which is this guy. That was 1 here. That's 1, 3, right? That point. We have then 1, 4, which you guys told me there, which is up here, right? And then you got me 1, 5, which is this point up here, right? Then you got me 2, 3, which is here. Run out of colors. You got me 2, 4, which is here. And I need more colors. Man, well, my bad. So I have to go back to blue again. This one. What? Wait, what? Whoop. Oh, hey, you guys tricked me. Why? Yeah, I was like, wait a minute, 1,2. You have not obeyed the rules. So some people like to talk about roster notation like getting into a nightclub or something. You know, like, this is like the criteria for the bouncer. You have to meet this criteria before they'll let you into the club. And 1,2 does not belong in this club because he has not met the criteria that 1 is an element of A. Well, that's okay, but 2, is 2 an element of B? It is not, right? So this was wrong. Yeah, we should put 2,5 there. So, of course, I knew it was wrong all along. I allowed it for your learning. So, and now you can, and also, by the way, you can understand why the number of things in A cross B should be the number of things in A times the number of things in B, because if you just imagine it in terms of like a grid, it's like the length by the height, so that's the number, just counting. So it's kind of cool. Now, okay, so you're like, but what does this have to do with the tangent problem and the area problem? Well, not too much, really. But what's most interesting is when we talk about, by the way, if, I'll put it up here. Let me just kind of weasel it into here. A cross A, we denote that by A squared, by the way. So a special case, when we have the same set cross Cartesian product with itself, then we just call it the set squared, all right? So like, for example, R cross R is equal to R squared, right? R squared, well, this is the Cartesian plane, right? So we can picture R squared as the xy plane. There's a one-to-one correspondence between R squared and the xy plane, right? Every point in the xy plane corresponds to x comma y. That is something in the Cartesian product of R with itself. Now, if you go on to take calculus 3, then we start looking at R cross R, which is R cubed, right? And or three-dimensional real space, and there's a one-to-one correspondence between that and like actual physical, typical, everyday geometry, right? You have like an x direction, a y direction, and a z direction. That's the kind of thing we study in calculus 3. But we'll keep it two-dimensional in here. So, oh man, I'm the worst. I'm sorry. I'm my own worst cameraman. I've been over here for the last 5 minutes. Yeah? Sorry about that. Hey, but you get what you pay for, right? All right, so moving on here. So I'm not going to write all this out, but I'd like you to look at page 17 and look at definition 2.2.1, all right? So definition 2.2.1 on page 17, I have listed the axioms for the set of real numbers. All right? So read through those. What do we say? So we have, what can we do with real numbers? We can add them. We can multiply them, right? There's a 0, there's a 1, there's a negative for every real number. There's a multiplicative inverse for every non-zero real number, right? There's an ordering to the real numbers, right? We have less than, we have greater than. If A is less than or equal to B and B is less than or equal to A, that forces A to be equal to B, right? There's this ordering. So I think if you look at it, axioms 1 through 10, they're pretty familiar. They basically just express what we know in algebra, that, you know, addition commutes, multiplication commutes, they're both associative, they have the distributive properties. These should all be familiar, happy facts, right? And then axiom 11. Axiom 11 right there, that's something a little bit interesting, right? Definition 2.2.1. So basically axioms 1 through 10, usual algebra, usual algebraic and inequality rules, right? Just to summarize, right? Axiom 11, though, and by the way, axiom 11, let's write it out. It says least upper bound property. And here's what that property is. It says that every non-empty subset of the real numbers has an upper bound, that has an upper bound has a least upper bound. So this axiom 11 is very special to the set of real numbers, okay? This captures what's called the completeness of R. Now, I understand it's just words on the chalkboard right now. Let me give you an example to explain what I mean by upper bound, okay? And while I'm doing it, let me also introduce the interval notation. I think you guys know interval notation already, right? So what does it mean for an upper bound? M is upper bound for set S if X, an element of S, implies that X is less than M. Oh, yeah, this is just my shorthand for definition. Yeah. I will warn you. I will also, without thinking, do this. That's equation. This is theorem. This right here, this is a shorthand that means implies. It's not the same as equality. This means that this statement, if this statement is true, then that must also be true. It's implication. So an upper bound to a set is a number which is larger than everything in the set. That's what an upper bound is. Okay? So to give examples of upper bounds, I really need to bring us into some of the interval notation. So like, what does A, B mean? A open interval A to B? This is X in the reals, such that what? Such that A is less than X is less than B, right? We call that the open interval from A to B. You've heard this before, yeah?
Yes.
Okay. There's actually a danger for confusion here, isn't there? Because this doesn't mean the open interval from 1 to 5, does it? Ever thought about this? We use the same notation for open interval that we do point. This bothers French mathematicians so much that in French mathematics, they'll instead do this.
That's weird.
But I can't bear it. I just say, you know what, we have two notations, but it is clear from the context whether we're talking about a point or whether we're talking about an open interval. But if you're ever in doubt, you are allowed to ask me for sure. Okay? Now, we also have what? Like closed interval, right? That just throws in the endpoints, right? And then you got like, let me not write down the definition on the board, but you know what this means. You know what this means, right? Whenever we write any of these things, we have presupposed what? A is less than B, right? Like, and then what else is there? We also have like A to infinity, right? We have A included to infinity. We have minus infinity to A. And we have minus infinity to A included. And we also have minus infinity to infinity, which is the whole real deal, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 different types. These are these are the so-called intervals. Intervals are the real numbers. Do you know how to characterize those in terms of a number line? What makes those sets different than other kinds of sets in the number line? So if you want to picture these on a number line, right? Like for example, from A to B, we do what? Like A. I mean, there's various techniques. Some people like draw the set over the thing, and then make it like bold like that, as a picture of the closed interval from A to B. You know. Other times, people like to use this picture for like the open interval. Right? I have these pictures in my notes as well. But the key thing, if you want to think about it geometrically, all of the intervals are sets that we can draw on the number line without lifting our chalk or our pen or a pencil. They're so-called connected intervals. There's actually one other. You know what else you can do without lifting what else you can draw on the number line without like lifting your chalk from the drawing? There's one other connected kind of interval. But sometimes it gets left out of interval, but it's just this. Just a single point. Right? That's also a connected subset of the reals. And this is we just write that in that case. This is called a singleton. A singleton is a set containing just one element. All right, so now I've refreshed your memory about this notation, so we're on the same page, we know what an interval is. Let me give you an example which illustrates some of what's going on here. I'll do a couple different things in this example. First of all, how can we get a singleton from a couple different sets? How about this? What if we took minus infinity to 2 included and intersect it with 2 to 3 excluded? Do you guys know intersection? Intersection is we take two sets, we look for all of the elements which are common to both, right? This is intersection. So which point is common to both of these sets?
2.
Just 2, right? So this is just that. We could also look at something like, let's see here, minus 3 to 2, unioned with 0 to 5. Now union is what we take. The union of two sets is the set of elements which are in one of the sets or the other. They can be in both too, right? It's not an exclusive or. So you can kind of you can figure this out with a number line, right? So you say, okay, well, -3 is over here, 2 is here, right? So this is a picture of that one, and then I can visualize 0 to 5 by like here over to 5, right? So what is the union of these two?
0, 1, 2.
So remember, if x is here, it's in the union, right? If x is in both of them, it's in the union. If x is just in the blue one, it's still in the union. If the point is in either of the sets, it counts, right? So not 0 to 5, but the
Union. I was thinking
union.
The
Oh, your intersection? Yeah, you said 0 to 2 for the 0 to 2 for the intersection. Yes, right.
I didn't hear you say.
Oh yeah, union. So what did you say? Did you say? Did you say? The answer? Maybe?
-3 to 2.
-3. I'll take the -3, but it goes past 2.
I mean, to 5.
Yeah, all the way to 5. Neither -3 nor 5 are included, but there you go, union.
That is weird to look at, thinking it's all included between those.
Yeah.
Thinking of it as a point.
Mm-hmm. Okay, so when's class end? Class ends at 1:45. Is that right?
Yes.
So I'm just about out of time, but there's something else I was going to tell you guys. Oh, I wanted to just give you this least upper bound property I was talking about, right? So if we look at the set, for example, 0 to 2, what would be an upper bound for this? There are infinitely many choices. For example, 3. 3 is, 3 is greater than x for x in 0 to 2, right? Because 3 is past 0 to 2. It's definitely an upper bound, right? What's the least upper bound for 0 to 2?
Natural numbers.
It can be, we're talking about real numbers. It is as easy as you're thinking it is. It's not a trick question. What do you think it is? Think it's 1? Oh, no, because 1 wouldn't work because 1.5 is bigger than 1, and 1.5 is in this set.
2.1.
Now this is not, so you might be thinking about this thing. But notice that this is all of the real numbers from 0 to 2 not included, right? So it's not, there's infinitely many numbers in this. What'd you say? What'd you say? 2.1. 2.1 would be another upper bound. You say you should choose m equal to 2.1 as an upper bound. But I can do better. I could make 2.01. That's also an upper bound, and it's smaller than your upper bound, so that can't be the least upper bound.
So would you do the limit?
It's 2, right? But it does kind of get at the idea of a limit, yeah. In fact, the fact that we have a least upper bound property for real numbers is what makes limits make sense. There's no holes in the real numbers. Now, in contrast, so you have a sense of why we need real numbers, do you guys ever look at the decimal expansion of the square root of 2? If you look at it, it's like 1.414, da da da. I forget. But if you just truncate that, like 1.4, is that a rational number? Oh, it's 14 over 10, right? 1.41 is 141 over 100. 1.414 is 1,414 over 1,000. Any truncated decimal expansion of the square root of 2 is a decimal number, okay? So if you take the set of all truncated decimals